Hello, everyone. I hope you're enjoying our very first Connect Online event. My name is Aaron Vinton. I work at Couchbase as a Principal Solutions Architect on the Professional Services team. I've been with Couchbase for almost 3 years now, and I've been working with the platform for about 6 years. Today, I'm going to talk to you about a topic that we regularly see in the field during customer engagements, which is how to identify, tune, and optimize slow-performing queries. For our agenda today, we're going to look at the query workflow, some available system Keyspaces to us, how to identify slow queries, how to tune those slow queries, some additional query insights and other considerations for you to think about. I always like to start off my presentations with a quote, and this is a great quote from Michael Fromberger that says, "There are only 3 optimizations: do less, do it less often, do it faster. The largest gains come from 1, but we spend all of our time on 3. So do less. Less is more, smaller is faster, and this is going to be the motto for our session today. We do have a demo cluster set up and running using multidimensional scaling as a best practice. There are 3 data nodes, 2 index nodes, and 2 query nodes. Additionally, we have 2 application servers that are running Nickelback. Nickelback is a CLI tool for stress testing the query and index services. It ships with Couchbase and can be found in the opt Couchbase bin directory. Each one of our nodes in this cluster have 8 CPU and 32 gig of RAM. Before again jumping in identifying how to find slow queries and how to tune those slow queries, it's important to understand the query workflow and how indexes are selected so we know where to apply our optimizations at. Now, this is the workflow that every nickel request from the SDK follows. The nickel query is submitted over the REST API to the query service. The query service will then read, analyze, parse, plan, optimize, and ultimately execute that query, performing an index scan, pushing down the index filters or spans to the index service. The index service will perform that scan, send back a qualified list of document IDs to the query service. The query service will then take those document IDs, go and retrieve those documents from the data service, bringing them back to the query service, in memory then applying any additional filtering, ordering, sorting, limiting, etc., before finally projecting the results back to the client and streaming them. While we won't have time in this session to necessarily cover every single possible optimization that we can do, it's important to understand when viewing the query pipeline that we can apply optimizations and tunings at each step along the way. With appropriate optimizations and tunings, we can actually eliminate almost all of these steps in the query processing pipeline. For index selection, indexes are selected based on the following rules. Online indexes. So this means any indexes that are in a pending or building state are not eligible for selection. Only indexes that are 100% built in online are eligible to be selected by the query service. Then we have preferred indexes. This is indexes with a use index statement or clause. Any index listed in here, as long as it can satisfy the query, will be eligible for selection. Nickel is not going to use an index that cannot satisfy the query. Then we have the satisfying index filters. This is the index where statement, so we can filter the index. I don't necessarily want to have every document in my bucket in my index. That index where filter must also be present or at least broad enough to satisfy the query. Then we have the satisfying index keys. So indexes whose leading keys satisfy the query predicates are selected. This is a common way to select indexes within B-tree indexes. Then we have lastly the longest satisfying keys. So an index that has keys A, B, and C would be preferred over an index that has keys A and B, if the query predicate was referencing all 3 of those keys A, B, and C. However, things like index key order or key cardinality, sort order, don't have an impact on index selection. This is because Couchbase is a rule-based optimizer and not a cost-based optimizer. So you follow these set of rules. That's the index that's going to be selected. We're not considering things like statistics, cardinality, etc., to determine which indexes are going to be selected. However, I should say that in Couchbase Server 6.6, there's a developer preview of a cost-based optimizer. The cost-based optimizer is scheduled to be GA with Couchbase Server 7.0 when that is released. There are many different Keyspaces available to us in Couchbase Server. For this particular session, we're going to focus on two of those, which is system completed request. This Keyspace holds all actively executing or currently executing queries and their plans. And then we have system completed requests. This Keyspace stores any requests that have run longer than a specified period of time or qualify for additional logging. These records not only contain the query that was executed, but also per execution metrics and timings. This can give you an idea of individual query performance, node health, overall cluster health, and performance. Upon receiving a nickel statement, it's immediately placed into the active request Keyspace. It is then parsed, planned, and ultimately executed. After execution, cleanup is performed. As part of this cleanup process, it's decided should this query be logged or not. If it is determined that this query should be logged, it is then written to the system completed request Keyspace. There are two main query settings that control the behavior of system completed requests. This is the completed limit and the completed threshold. The completed limit says how many records should I save, and the completed threshold is the duration that if a query is longer than that duration, it should be logged in system completed request. The default limit is 4,000. This is per query node. So if I have 4 query nodes in my cluster as an example, I would have a total of 16,000 completed requests available to me. The threshold, on the other hand, is 1,000 milliseconds by default, or 1 second. So any query that takes longer than 1 second to execute will be saved in system completed request by default. And you can change these settings as of Couchbase Server 6.5. In the UI under the Query Advanced settings, you're able to set both the completed limit and the completed threshold. We can query system completed requests just like we would any other bucket in Couchbase Server. The documents and the attributes that are returned from system completed requests can be treated just like any other document or attribute from a bucket or a nickel query. We can filter on these attributes. We can order on these attributes. We can project these attributes however we would like. There's a ton of really valuable information that's available to us in system completed requests. Things like the elapsed time. How long did it take from when the query service received the query until it sent a response? Things like the phase counts, the number of documents processed between each of the operators, the node that actually executed the query, the number of results, the size of the results in bytes. We have things like the service time. So we can calculate the delta between elapsed time and service time to give us a queue time. A high queue time is an indicator that as your nickel queries are coming in, they're spending a lot of time waiting to be executed before subsequently being executed. So if we start to see a high queue time, that might be an indication we need to add more query nodes and scale out horizontally. We can see the actual nickel statement that was executed, or the RBAC user that sent that query, the IP address that that query came from. So there's a ton of really valuable information in system completed requests for us to use. So how do we start using this to identify slow or resource intensive queries? Where should we focus our efforts at? Enter the Pareto Principle. This is also known as the 80-20 rule that states for many events, roughly 80% of the effects come from 20% of the causes. If we apply this to our queries, we can restate that as roughly 80% of our problems are caused by 20% of our queries. So if we initially focus on and tune those 20% of our queries, that's where we're going to get the most return on investment. And typically this is going to be number one, the longest running queries and the most frequent queries. So how do we go about finding the longest running queries in system completed requests? This is a very common statement that I use with customers. So in this example here, we're returning the statement, the average execution time, and the total number of queries. We're filtering out certain statements like advise, infer, index, etc., as these statements cannot be tuned. They're more administrative in nature. Then we group by the statement. This way I can group all the common statements together and find an average execution time. So I'm not just looking at the mins or the maxes as an example. Things like service time and elapsed time are both string duration values, so 1.2s. We need to convert those to an integer value, a numeric value that we can actually use to perform sorting on. And lastly, we're going to order by the service time descending so that we have the longest running queries first. There's actually been load that's being generated against our demo cluster, and we can execute this query here and see what slow queries that we are able to find. So we can see we're doing 1 or 2 nickel requests per second here. We're doing around 140,000 get operations per second with the load that's being generated. I can execute this query and I'm able to find, these are the 5 slow queries that I've found in my cluster. I can see that for this particular query here, I've seen it 332 times and it's executing in an average of 46 seconds. One of the fastest ways you can get started is simply by taking a statement, pasting it here into Query Workbench, and clicking on the Advise button. This is going to do some inferring behind the scenes, some sampling, if you will, to determine, analyze your query, and say, here's the best index I can recommend that you create. And in this example, it comes back and says, this is the index that's currently being used. Here's a recommended covering index, and here's a recommended secondary index. Right from the UI, you're able to click on Create and Build. We can build that index from the UI. Index Advisor is going to be a great way to get started on there. But we still should go through that tuning, testing process, verifying the results that we're seeing from what Index Advisor is ultimately recommending for us to use. After tuning and focusing on the longest running queries, the next set of queries you're going to want to look at will be the most frequent queries. These queries might not be the slowest or the fastest or necessarily the most resource intensive, but because they occur the most often, by tuning these, we can make better use of our resources and focusing on them. We can also identify the largest queries based on response size. So queries with a low number of documents but a high result size is an indication that your documents are too large. And these types of queries can benefit from returning just the meta ID or document ID and then having the SDK asynchronously go and retrieve each one of those documents. This will ultimately use less memory on the query nodes, allowing you to do more, allowing for greater throughput and better utilization of your resources. We can focus on queries that have the largest response counts. Queries that are returning hundreds of thousands of documents, for example. Queries with high result counts are going to be great candidates for things like potentially implementing pagination or batching or bulk get style operations. We can find low selectivity queries, and we'll talk a little bit more about selectivity here in the next section, but this is basically referring to the number of results that are sent back to the client versus the number of results that came out of the index scan. For example, if my index scan returned 100,000 items, but I only sent back 10 items to my client, that's not very efficient. We want to have a query selectivity value of 100%, meaning 100% of the items that came out of the index are returned back to the client, so 1-to-1. We can actually combine all of these statements into a useful debugging query. We can execute this query from the Query Workbench. We can call the nickel REST API directly, or we can even build some type of application around this or reporting strategy around this. Now that we've identified our slow performing queries, we now need to tune them, right? And tuning is an iterative process. So number one, identify, we've done that. Now we need to verify the execution plans that are produced by the optimizer and look for places to implement additional tunings and or optimizations. And explain is going to be the key there. You want to use the visual explain or the plan text to identify where those bottlenecks are. And then lastly, we will implement corrective actions to generate better execution plans for poor performing nickel queries. And remember again, Couchbase is a rule-based optimizer, not a cost-based optimizer. Key and index cardinality do not have an impact on index selection. The order of the fields in the index is going to be up to you to choose. So what is cardinality? Cardinality is referring to the individual uniqueness of values in a specific data set. An example of high cardinality would be things like an email address, a username, a GUID. Normal cardinality is going to be first name, last name, city. Right? There's some uniqueness, but not a lot. And low cardinality is going to be things like a status field or a Boolean field. There's not a lot of possible combinations for low cardinality. Along with cardinality, we have selectivity. And selectivity is used to measure the variation in unique values across a data set. A bucket is a data set. An index is a data set, right? It's a smaller subset of your data. A query is a result set. A query result set is a data set. And we can use selectivity to calculate the performance, good or bad. And we roughly calculate selectivity as the number of distinct values divided by the total number of records. And when it comes to index and query tuning, there's two particular selectivity measurements that we want to look at. Number one is going to be the bucket or projection selectivity. This is the number of documents that are in the bucket that qualify for the index, that satisfy the index filter. This is often referred to as index segmentation. I don't want to have, if I have 100 million items in my bucket, I don't want to have 100 million items in my index. I want to create a more efficient index that's smaller and targeted to the question that I'm asking. Then we have index selectivity. This is going to be a measure of the unique values in the index compared to the total number of entries in the index. And if you're trying to get to optimum performance, you want to have a relatively low bucket selectivity, as this means your index is going to be smaller, and you want to have a higher value for index selectivity, as this means there's a lot of uniqueness within that index or data set. So let's walk through a tuning example here and calculate the bucket and index selectivity for various different indexes. In this example, the query is relatively straightforward. We're selecting the airline ID, the call sign, the country, and the name from the flight data bucket, where the doc type is airline and the IATA code is equal to UA. And we can execute this query here. We will actually stop the load that's being generated against our cluster and execute this particular query. It should take probably around 6 to 8 seconds or so for that to execute. And what we're going to do now, we see that it takes 6 seconds just to execute from Query Workbench. We're going to execute this query using Nickelback over and over and over again. And this query is currently using a primary index scan. As this query is being executed, we can look at things like the number of get operations per second. We can see those are relatively high. We can look at the CPU usage on our query nodes here and see that it's over 90%. We can look at the CPU usage on our data nodes and see that it's 30–40%. So we're generating a tremendous amount of load against the cluster, but the number of nickel queries per second is maybe 1–2 nickel requests per second. So to calculate cardinality and selectivity, we need to know 3 things, which is the total number of documents in the bucket, the total number of documents in the index, and the total number of unique values within that specific index. So the total number of documents in our bucket in this case is 188,266. And this index here, this is a doc type only index. This is probably the most common index that we see. It's something that's easy to create. Every query will work as long as there's a doc type predicate that's specified in the query. And oftentimes this query will even satisfy performance considerations in lower environments because there's not a lot of data, right? The use of a doc type attribute is a great best practice to implement from a data modeling perspective. However, as soon as we create this style of index against a larger data set, problems start to arise. Queries start to perform slowly. So in this case, for a primary index that we're currently executing, that's equivalent to a full database scan in a relational system where we perform a full table scan against each and every table in the key space. A doc type only index is the equivalent of a table scan in a relational system. Let's go ahead and create this index here and see what we get from a performance benefit, if any. So we're going to create this index here. It's being built. I'm using a replica because I have 2 index nodes, which means each indexer will have a copy of the index. And you can see here the number of requests per second has gradually started to increase from 2 to 4 to 5, 8, 9, 10 requests per second. So that index did help, but let's look at the bucket and the index selectivity values here for this particular index. In this case, the bucket selectivity is 100%. That means that all of the items in the bucket are present in the index. The index selectivity is 0.004%. I only have 8 unique values within the index. This is the complete opposite of what we said we needed for optimal performance. Remember, we want to have a low bucket selectivity and a high index selectivity. This is not an index that I would recommend that we create. For querying index performance, it's going to follow physics. There's 2 basic rules here. We can say quantity and quality. Quantity, less work is more performant, and quality, efficient work is more performant. And query processing is no different. It tries to optimize both of these factors into various scenarios to bring optimizations and efficiency, right? Less is more. So how can we apply the concept of less is more? If we remember, our query had 2 predicates where doc type equal airline and IATA code equals UA. So in this case, let's create an index on the IATA code. And if we look, we'll notice there's only 61,432 items in the index instead of 188,000. This is because not every document in our bucket contains an IATA field, right? But it did contain a doc type attribute. Remember, smaller is always going to be faster. And we also look at the number of unique values in this index. We have 10,180 values in this index, up from 8. So mathematically, it appears that, again, this is going to be a better version of our index. But let's create this index here and try it out and see what performance benefit we get by using an index now that has a higher index selectivity and a lower bucket selectivity. Currently, we were at 20 requests per second, and now we can see that index is being built. Same load being generated, same hardware being generated, but now instead of doing 20 nickel requests per second with that one query, I'm doing over 7,000 nickel requests per second. That's a tremendous difference in performance. But we can still do better. In this case, every index in Couchbase should be a partial or filtered index. I want to add an index predicate in this case to say where doc type equals airline, right? Our query, we know, only ever cares about airline documents. It doesn't care about any other type of airline documents. And if we don't care about those, why should we index them? This is a common optimization mistake. Right? If there's only ever going to be one value, that value doesn't need to be in the index itself. Right? More often than not, I'll see an index that's doc type, comma, IATA code. Well, I'm putting doc type, a value that I only ever cared about one value, first, where I really know the IATA code has the uniqueness. So because there's only ever one value, I can simply make it an index predicate. I don't need to actually index that value. We're telling the indexer only if the doc type is airline should you index the IATA code in this case. And look at the index count. We went from 61,432 down to 6,161, reducing both the bucket selectivity and increasing the index selectivity. So thinking about this particular query, is there any more possible optimizations that we can make? Oftentimes when you're tuning queries and indexes, you get too focused on the query or the index, and we forget about the other component, which is the data. So let's take a look at the document that we're querying here. In this case, our document contains an active attribute. Does our application query actually care about inactive airlines at all? Now, this is an assumption, but more than likely our query doesn't care about inactive airlines. It only cares about active airlines. So we can add an additional index predicate, in this case of and active equal true. This would require us also to add that predicate to our query, but we can make that change very easily. And now this reduces our index count even further, from 6,161 all the way down to 1,254. Our bucket selectivity in this case has decreased to less than 1% at 0.66%, and our index selectivity has gone from 18% in the previous example to almost 80% at 79.26. Now we're really starting to achieve that optimal performance for our queries. But what else can we do? Is there anything else outside of these queries that we can do instead of creating an index, for example? Remember back to the beginning of the session, we looked at the query pipeline. And up to this point, we've eliminated or tuned specific steps in the pipeline by looking at just the query and the index. There's still actually a couple phases here, though, that we can eliminate, specifically the parsing and the planning phases. And this is where prepared statements come in. So building and planning execution plans can be, for a nickel query, can be really fast, number one, but it's also resource intensive. And this is going to add repetitive processing and overhead to our queries. Every single time the query comes in, I might pass a different value, but I'm having to reparse that value. What we can do is prepare these often used queries or cache that plan so that once we've seen it once, any subsequent queries coming in can take advantage of that plan, eliminating the need to have this repetitive processing. And queries that use dynamic variables, for example, they're considered the same query for planning purposes. It's just the spans, the index filters that are being pushed down that are ultimately different. So for our query to properly leverage prepared statements, we first need to update it to use a bind parameter. This way we can have a dynamic value for the IATA code, but have a single prepared statement. If I was using just a constructed or raw query here, if I passed in UA as an example, and we prepared that statement, then I had another airline come in, AA, and I prepared that, I would have two separate prepared statements, but I might not ever see that query again. But if I use a bind parameter, I'm able to reuse that value and simply pass in a dynamic value to that. Bind parameters are also good from a best practice standpoint around security. Just as SQL injection is a thing, nickel injection is also a thing. We don't want somebody coming and trying to inject a malicious statement into our nickel queries in this case. So to prepare our query here, we're going to simply say prepare from demo. In this case, I'm using a named prepared statement. You can also do prepared statements from the SDK by simply setting the ad hoc parameter to false. And then the SDK will manage the life cycle of that prepared. So let's create our prepared statement in this case. And I'm going to go ahead and create the index that from the previous example where we added this active filter in here as well. We've created that prepared statement. Now we can execute our prepared statement. And you'll notice here in the UI under settings, I've added a named parameter of IATA with the value of UA. I can execute this query here, and we can see that it's on average probably 3-4 milliseconds. And we are still generating that load that was there. So we'll stop this, and now we will generate load with the prepared statement that's on there, right? Look at the query throughput now with prepared. I'm doing a 15, 16, 17,000 nickel requests per second, where previously all I was doing was maybe 7,000 nickel queries per second. Same query, Same hardware, now that we're using an optimized version of the index and we're preparing those nickel statements, I'm getting far greater throughput. By actually asking the query service to do less, I'm getting more throughput in this instance. So speaking of less is more, remember the query workflow that we examined at the beginning of the session? What if we were able to eliminate an entire service call from the query? Again, that would follow our motto of less is more. In this case, we can also implement a covering index, right? So when we create a covering index, the index not only contains all of the predicates, but it also contains all of the projections or values that are present in the select. And if the index contains all this information, there's no reason for the query service to go to the data service and retrieve any additional documents. It can get everything it needs from the indexer. So let's build this covering index here, and we will re-prepare our query. So again, same load still being generated. I'm going to build that, that version of the covering index. Then you can see here we're re-preparing our query. I had to re-prepare the query because the old query was pointing to a non-covering index. Now that I have prepared that query, we were actually able to get another roughly 3,000 or so operations per second. You can see from our baseline here, we were around 15,000, and now we're 18, 19, almost 20,000 queries per second. So we've been able to eliminate every step in the pipeline now, except for the scanning and the projection phases. Again, this isn't to say there's problems with these other steps. Nickel has an amazing feature set and is really, really fast. But for this particular example, we didn't need all of those features. And by eliminating those, we were able to get a tremendous performance improvement. By doing less work, we were able to increase our overall throughput in this case. So to recap what we saw here, we started with a response time of 6 seconds and a query throughput of, let's call it 1 query per second. Through an iterative process of query and index tuning, we were able to decrease our bucket selectivity from 100% to 0.66%. We were able to increase our index selectivity from 0.004% to almost 80% at 79.26. We implemented a prepared statement to save on query processing and planning time. We added a covering index in this case to eliminate an unnecessary data service call or fetch operation, ultimately ending with a response time of around 2 to 3 milliseconds and a query throughput of 20,000 queries per second. And if that's not worth a party parrot, I don't know what is. All right. So when it comes to tuning, remember optimal indexes for optimal performance. Smaller is going to be faster, less is going to be more. Drive your queries to the most selective index. Use explain and the visual explain to understand where your bottlenecks are. Get started quickly by using Index Advisor. Definitely avoid the use of a primary index in a production environment. Remove any unused indexes. You're spending all of this time tuning. Don't forget to clean up that technical debt, because there's still resources that are used to manage an index, even if that index isn't ever used. Every index you create should always be a partial or a filtered index, right? This leads to a smaller version of the index, a more targeted version of the index. Indexing, again, is not an alternative to best practices. You should be using things like bind parameters and prepared statements to get the most out of your resources. And not every query needs to be covered. A fetch isn't always a bad thing. If my index is selective enough where it only returns back a single item from the index scan, and I have to go fetch 1 item, 2 items, 10 items, however many it may be from the data service, that might meet my SLAs just fine. I don't need to necessarily create a covering index because there's a trade-off. A covering index is going to be a larger index, which means it's going to use more resources, but you have the advantage of eliminating that scatter-gather approach. However, if I have a query that returns 100,000 items from my index scan and I have to go fetch 100,000 items, that could have a dramatic effect on overall system performance. So take this on a case-by-case basis, but remember, not every query needs to be covered, but you can definitely gain some big performance benefits by covering your queries. And lastly, remember index key order and cardinality can have a significant effect on query performance. We saw this going from a doc type attribute with 8 unique values to an IATA attribute with 10,000 unique values. Index keys should be ordered based on the predicate types from the query in the following order: equality statements first, then end statements. This is basically an equality with an or. This equals this, or this, or this. Then less than statements, between statements, greater than statements, followed by array predicates, and then any other additional fields that can be used to cover the query. For keys that do share the same predicate type, equality especially, that's when things like cardinality is going to come into play. Right? Index Advisor will use these rules along with sampling again to make index recommendations. And Index Advisor is only going to get better and better and better as the cost-based optimizer is released with Couchbase Server 7.0. So up to this point, we've seen that queries that are able to be logged in system completed requests if they exceed an elapsed time, if they exceed that completed threshold value for the query service. Couchbase Server 6.5 introduced logging qualifiers. And logging qualifiers provide us the ability to add additional conditions outside of the execution time or the threshold for when a query should or shouldn't be logged. This will allow us to optionally log things like a specific IP address or from a specific user, or queries that generated a specific error. We can add logging qualifiers by calling the Nickel Admin REST API and using the plus sign to add them, using the minus sign to remove them. Now, logging qualifiers are evaluated using a logical OR. So for this particular example, we will save the query in system completed request if the user is tracking service or the IP address is 192.123. Logging qualifiers also are per query node. They are not global. So if you wanted to log this for each and every query that came in, you would need to execute this statement against each query or Nickel Service REST Admin API in your cluster. Additionally, we also have tagged sets. Tag sets work with logging qualifiers, but they allow you to evaluate these qualifiers using a logical AND. So where all these qualifiers must evaluate to true. A note about tag sets: you cannot have multiple values for the same qualifier. So I can't say tag this where the user is this or this. If I needed to do that, in this case, I would create multiple versions of the tag sets. If we do determine that we need to save a query that was tagged, we will also write an attribute into system request that is the name of the tag that was specified. And here we can see an example of creating a tag for any query that is the user of tracking service and the IP address is 192.123. This can be very useful for targeted debugging or tracing of a specific issue from a user or a specific application, etc. And then we can subsequently remove that tag set by removing all of the qualifiers. And to look for a tag set in system completed request, once we've created it, I can simply add a predicate of where tag equals name of tag, in this case, debug tracking issue. We also have profile timings. So you've probably seen profile timings if you've ever looked at the visual explain plan in the UI. This contains per execution timings as well as phase counts, etc. However, if for Nickel requests coming from the SDK, profile is set to off. In the UI, profile is set to timings, right? So profile can be set to timings on a per request basis. And when we query something like system completed requests, if a query that came in with profile set to timings, we would actually take that execution plan, that full execution plan, all the timings, all the counts, and we would store that in system completed requests. Now, enabling profile timings does not have an impact on performance, as every query in system active requests, meta.plan is always available. The impact will really come from resource consumption, memory consumption for having to store that plan for each query. So something useful, but use that with caution. the last insight that we have here is called controls. So when we're debugging, identifying slow queries using bind parameters, each query is the same. All we see is that bind parameter that's there. This gives us an advantage when we're querying system completed requests because we can perform aggregate functions grouped by operations against those, but we don't know the individual values that was used. You could have a situation where if the value is A, the query runs fast, but if the value is B, the query runs slow. Same index. Why is that? We can dive into that and determine these instances by setting controls to true. When controls is set to true, and we determine that, or first, as part of the response of a nickel query, the query service will send back a controls attribute with the actual values that were passed in. But if we logged that query in system completed request, we'll also store a controls attribute as well. And it'll look something like this. So in this example, I'm just calling the nickel query REST API to execute a query. As part of the response to that query, along with the results and metrics, etc., I'm getting a controls attribute back. Inside of that controlled attributes, I see a named arg attributes. And then I see the actual value of IATA and the UA value that I passed in for that. This can be really useful for debugging. And lastly, we have some additional considerations. So when identifying and tuning slow queries, here's some other things for you to think about, specifically when you're querying system completed requests. Each query node has its own version of system completed requests. These are queries that are requests for that specific node only. Not every query is stored again, only ones that exceed that threshold or meet additional qualifying logging qualifiers. Not every query, the completed requests that are stored on each node are in memory. They are ephemeral, which means if you restart the query service, you don't have any more system completed requests on that node. If the completed limit has been exceeded, the oldest records are purged to make room. We will never exceed that completed limit value. Queries against system completed requests perform a primary scan. So whatever node received that query has to go to the other node to retrieve the completed requests. And we'll look at that next. And lastly, you cannot create any indexes against the system completed requests keyspace. So when querying system completed requests, the query node 1 is going to receive that query. But what it has to do is a scatter gather. It needs to go to query node 2 and retrieve all of its completed requests. So in this case, 4,000 records. Query node 2 is going to send 4,000 records back to query node 1, which will then union its completed request with query node 2's, then applying any additional predicates, filtering, sorting, ordering, etc. So we'd be working with 8,000 records. And that might be somewhat fast with 2 nodes, but what if we had 6 nodes? Now query node 1 has to go to 5 additional query nodes, retrieving up to 20,000 additional records. This can be very resource intensive and time consuming as we continue to scale out, adding the number of query nodes. So one option for you to consider here is to actually lower the completed limit value to stay around, let's say, like 10,000 completed requests total across all of the query nodes in the cluster. That's one option. However, there's another option that I prefer, which is to limit the scope of the completed request query. And in this case, I can introduce a predicate that says node equal node name. The node name function will return the name of the query node that is executing that query, and subsequently limit the results to just those that are in the system completed request keyspace on that node. We know SDKs are going to distribute requests amongst all of the nodes in the cluster, so the likelihood that I would miss a request is very, very small. And if I needed to, I can still address each query node individually in the cluster, but I have limited the scope of that. If we add this to our long-running query on a specific node example that we saw from earlier in the presentation, we can actually take this query and execute that. And we can see here the results come back in about 60 milliseconds, under 100 milliseconds. But if I remove this attribute and we execute that particular query. It has to go to the other query node, fetch all of those documents, and this query took 4 seconds, 4.7 seconds. So it's going to be faster to limit the scope of the results. Again, deal with a smaller data set and go from there. We can clean up system completed requests. So if you've gone in and tuned a bunch of queries, you can actually delete them from system completed requests so you no longer see them anymore. And you can delete just like you would from any other bucket, whether this is by the request ID, a specific statement, etc. We can always delete from system completed requests. And you can actually delete from system active requests as well. By deleting a record from system active requests, this is effectively going to cancel a query. It's how you would stop a long running query. Some additional resources for you guys. All of the queries examples that I've shown and a whole lot more are available. They're up on my GitHub. If you go to developer.couchbase.com, here's a link to a nickel tuning guide. I'd strongly encourage you to download that, read through that, follow those learnings. We have learn.couchbase.com from our training services team. We have 2 specific courses related to nickel, where you have CD210. This is going to be Couchbase NoSQL data modeling, querying, and tuning using nickel. And we have our advanced course, CD410, Advanced Nickel Workshop, Tuning and Optimization. And lastly, we have professional services. So the professional services team, the team I'm on, if you have a new application that you're wanting to build, you want to get started with your appropriate queries, indexes, data modeling, access patterns out of the gate, get in touch with us. If you have existing queries and indexes that are slow and you need assistance tuning those, you get with our team, get with your account executive, account rep, and we'll be more than happy to work with you. And that's all I have for the presentation today. I appreciate you guys tuning in. Thank you very much for attending the Connect Online event, and I hope you enjoy the rest of the conference. Take care.